Okay, then this will be second part of the theory session number 1. Yeah, we are still working on the cumulant method, which is the central method used in the VirtualFluids code. So later today, if I still then have time and you're not all running away, I'm telling you exactly how we compute the central moments. But first of all, or the cumulants. First of all, let us try to understand how cumulants can be computed a little bit more efficiently, and then even more efficiently in the afternoon, or in section 2, I think. Let me see what this is, afternoon or not. So cumulants in terms of central moments. So I actually didn't talk about central moments at all, but the moments that we have derived previously, these raw moments, they are moments in the Euler frame, yeah, because we have to assume a certain frame of reference in which we take the integral over the velocity space, yeah. And this frame of reference is the resting frame of reference. Yeah? So we could say these are given in the Euler frame. Say in Euler frame we have F, and then we can also write moments in a Lagrangian frame, and we call this F now in a Lagrangian frame. So this is the same thing. We're moving the population. We are moving the origin of our coordinate system into the center of the population, the center of the distribution in the velocity space, such that their first moments will always be 0, centered. Yeah. So this is done here by. So you may know how you move. How you move something in a so you're moving a coordinate system of a Laplace transform by this multiplication by e by the power of u and c. So this is a little bit basic theory on Laplace or Fourier transform. Yeah. So if we move the origin of our coordinate system, yeah, in the Laplace transform, so what happens to our cumulants? So if you write down the definition of cumulants, and we take now the logarithm, not of f, but of f with this snake, u e by the power of u times c. So this is the moved coordinate system, and this again we evaluate this xc equal to 0. Now we have a logarithm of a product, and then we have a logarithm of an e function, right? So what would this give us? This gives us this everything that's been in front onto u times xc plus the logarithm in the other frame of reference, in the centered frame of reference, and here xc is again equal to 0. So now here you have a linear function, and you take the derivative of it, and then after this you also take xc equal to 0. So this will be non-zero only in the first derivatives, obviously, right? So you get that this is what you expect from quantities that have been designed to be independent of each other, right? All but order 1 cumulants are independent of velocity. Or you could say all of them are independent of the frame in which they, so they are frame independent, yeah, frame. So, and therefore, it's more convenient to use central moments. So central moments, I write them with K, A, B, C. And they go as the sum A, B, C. So they go here from -1 to 1, F, I, J, K. And now instead of having here I, we have I minus U, the x velocity, by the power of A, J minus V by the power of B, and K minus W by the power of C. And the implication is that we choose K110 and K010 and K001, that we choose all of them to be 0. This is how we choose the velocity. And then, for example, if you write C002 as we have seen, is M002 divided by M000 minus M001 squared divided by M000. Now, all of this, yeah, cumulants can be derived in any frame of reference. So I can replace all the m's with k's, yeah, because in a different, I can just derive them in a different frame. Because it's not a first order cumulant, it's a second order cumulant, which is frame independent. So we have K002 divided by K000 minus K001 square divided by K000. And you know that this is 0, and therefore this is K002 divided by K000. And the higher the order of the cumulants, the more terms will disappear like this. So you can, reduce the amount of calculations because cumulants get the equations get very, very big. But if you do them in central moments, then you can delete many of these terms. Please.
That's IJK.
IJK.
We somewhere IJK.
Oh, yes, that's absolutely true. IJK. So then we are talking about virtual fluids here. So in virtual fluids, there are variants. There's one variant is called K15 compressible Navier-Stokes. We write it out, right? Navier-Stokes. So it's called K. I don't know how cumulants are written in Danish, but in German they are written with a K. So we try to separate them from central moments, which we write with a C, and unfortunately we write central moments with K and cumulants with C. Lot of confusion, yeah, but the K means cumulant. Actually, this was not my invention. Others call this way. Others outside our group. So K15 means the paper that we published in 2015. In this variant, the relaxation rates of all these of all cumulants that are not related to shear viscosity are set to 1. So this way, this thing is now very stable. It's not necessarily the most accurate way. And okay, putting everything that you don't care particular to equilibrium, this in Letters-Boltzmann is called regularization. Regularization. Okay, the definition. So the definition is that everything not related to the shear viscosity is put to equilibrium. This is called regularization. And there are, there are many this methods: regularized Letters-Boltzmann, recursively regularized Letters-Boltzmann, hybrid recursively regularized Letters-Boltzmann. So there are plenty of these things. We also have one which we don't call that way. Just you put the relaxation rates to 1, then you get this behavior. Okay. So this is very stable. This is why these things are also very like the in this French code. If somebody helps me, what is the name of labs? Or I never remember whether this is the old name or the new name of this code. No. The one from Marseille. Pro LB or labs. So one is the old name and one is the other name. Yeah. So they use regularization. Right. So this is not necessarily the version that you want to use. If you use VirtualFluids, the one that you want to use is potentially the K17 compressible Navier-Stokes, because this is using something that we call superconvergence. Of course, we call it this way because it sounds good, but it also is good. So what we mean by superconvergence? Okay, this is one of the most terrible paper I've ever written. I think it's completely unreadable. I'll try to be brief, but to get across what is happening.
Sorry, I know you don't like questions, but these compressible Letters-Boltzmann,
yeah.
Can they also simulate shocks?
No. Okay, so what is indicated, because so there's a lot of nomenclature going on in the Letters-Boltzmann world, of course. Yeah. This is called compressible in order to distinguish it from incompressible, where in the Letters-Boltzmann world, and this is not according to how you actually should name this, there is the concept of distinguishing the variable density version of the equilibrium from a constant density version, which both of them are as compressible as the other. Yeah, but unfortunately, the one is called the incompressible and the other one is called the compressible. This doesn't have anything to do with what in fluid dynamics we consider to be really compressible fluid dynamics. Yeah. So this is nomenclature out of Letters-Boltzmann history. It's called that way because we also have constant density versions of these kernels. Yeah. Okay. So okay, one sentence here. By Taylor expansion of the Letters-Boltzmann equation, that was equation number 1, the only equation that we numbered. What I'm doing. So there we want to determine what we call the linearized the linearized leading order, linearized in terms of Mach number. Because we have now, the thing is we have several errors. One is a Mach number error that comes from the from the compressibility and that we do not conserve energy and so on. Yeah, this leads us to Mach number error. And this error is not under our control by the relaxation rates. If you want to get rid of this, you have to do something else. Yeah. So in order so that we need to separate these two things, and this is what we mean by linearized leading error in the resulting Navier-Stokes equation. So what we obtain is we get a Navier-Stokes equation and say we have a Navier-Stokes equation we have the part of the Navier-Stokes equation in x direction. You can also write this in y. I mean, due to the symmetry of the lattice, they will all behave the same way, and all of the problems are solved together in that way. Yeah. So you get this thing. Then you have Mach errors that we ignore, and in addition to these Mach errors, we also have spatial discretization errors at the leading order. So we had in the Navier-Stokes equation we have second derivatives, yeah. Then we are second order accurate, and then which means we have discretization orders of order 4 in the derivatives. So basically, what you get is you get a function g1 times a function of the relaxation rates. Everything else is constant, yeah, and the part that is not constant is you get the forced derivative of u plus in z direction, and the forced derivative in y also on u with one prefactor here, and you get a g2 that comes with the forced derivative dyy z also on u, plus a g3 dxy z on v plus dxy z on w, plus g4 on dxxy u plus dxx z u plus g5 on dx4 and u. So actually getting these equations requires doing the Taylor expansion, putting the Navier-Stokes equation into itself again and again until you get all these terms out. And I mean, there's no, the reason why there is no time derivative in this is whenever you have a time derivative of a velocity, you can substitute the Navier-Stokes equation again. So in order to eliminate and put everything in the spatial derivatives, right? So, and these things remain here, and these functions gn, and these are just functions of relaxation rates omega 3, omega 4, and omega 5, and something. And now we have a problem. So, because originally they are just functions of these three relaxation rates. Now, problem is there are 5 of them. They are all different, and they depend only on 3 of the remaining relaxation rates. So we actually have 10 relaxation rates open, yeah, of which one we need for viscosity, the other one we need for bulk viscosity. So we would have 8 free rates. But unfortunately, the leading order error depends only on 3 of them. Yeah? So then this is not, unless we are extremely lucky, this is not enough to eliminate these errors. And therefore, we need something else, and this something else we call A and B. And this is something, let me write down this omega 3 is the relaxation rate for these are all third order cumulants. So C1, 1, 2 plus C1, 0, 2. Yeah, so the sum of these two, they relax with omega 3. Then, I mean, you have to be diligent here before, yeah, because you have to identify what you can, relax with different rates. Yeah, so you would set omega 4 to C1 to 1 to 0 minus C1, 0, 2. So we have once the sum and once the difference, and then we have omega 5 is the rate for C1, 1, 1. Actually, physically speaking, this thing here, the difference between the two and this here can, by rotating by 45 degrees, be put onto each other. So physically, they should have the same relaxation rate. However, the lattice is anisotropic in itself, yeah. So the lattice already produces some anisotropy, and we decide on different relaxation rates to compensate for this anisotropy here, yeah. So I mean, you have one anisotropy from the relaxation rate, you have another anisotropy from the lattice. You put the two together to somehow squeeze the last bit out of it and make it isotropic. Right, so the leading order error depends only on the rates of the third order moment. So this is, I have to say, even though I'm getting up my time, I mean, the question whether you could choose the relaxation rates in a specific way to get rid of all the errors, this has been around for 25 years. Yeah, it's called the magic parameter, the quadric parameter, whatever you like. Yeah, and there was always some cases, some specific cases where you put, for that specific case, you have to put that specific relaxation rate, then you get the exact solution. Then you turn your problem by 45 degrees, then you need a different relaxation rate, yeah? So the problem was, after people looking for 25 years, you would damage your reputation if you admitted that you're working on this thing, yeah? So I kind of tried to, because then my then PhD student, he checked this out and said, when I put these values like this, then the result is so much better. Okay, I sit down with you and I try to prove to you that this is impossible. So, and you can actually derive that there are 5 of these terms pretty easily, just from symmetry arguments. Yeah, but in order to know how these things look like, you have to do the Taylor expansion, the substitution, going on and going on and going on. And I tried. I mean, the first time this worked was when my computer had 16 gigabytes of RAM. Because before this, Mathematica would not converge on this. So this was necessary. So I try to prove. I mean, it's pretty obvious, yeah. So you get these 5 guys here. You can actually prove from other simple arguments that they can only depend on third order moments, not on third order relaxation rates, not on others. So you will only have 3. And you will have to eliminate five guys. So you must be extremely lucky. So you have to write this out and see whether you're lucky. Now you write it out, you see you are not lucky. And then you look again and see, why then? I see what it's depending on. Because it's depending on the equilibrium of the first order cumulants. The equilibrium of first order cumulants should all be 0, physically speaking. But, it's anisotropic because the lattice is anisotropic. So maybe I pour some more anisotropy in this by design. to get rid of this anisotropy. And the way we do this is, so they are first order cumulants like this one. Now I'm a bad guy because I'm now calling this, okay, I should, there are too many professors here. So I eliminate equilibrium and I write attractor. Yeah, C2, this first order cumulant C220. Yeah, I say this is attracted to A. I don't know what A is. C200 plus C020. Yeah, so they are dependent on the. I mean, these guys themselves, when they are in equilibrium, they are zero. Yeah, so then if they are at equilibrium, they would disappear and they will give you zero, but they may not be at equilibrium. And then we have C. Okay, I write one more. The others, I mean, to me symmetric, this would look like this, yeah? And the other one you get as homework. Then we also have the other first order cumulant, C211 attractor, and I say, well, we make this B times C011. Okay, so I just do it. For whatever reason. So the reason, of course, being that now this Gn also depend on A and B. Because in here are second derivatives of velocity. Yeah, so these guys here include second derivative of velocity when they are not in equilibrium. If they are in equilibrium, they are zero. So this means now they are actually functions of all of this. And now what you could try is to solve G1 equals to G2 equals to G3 equals to G4 equals to G5 equals to 0. Okay, you can try this. You find this doesn't work very well. So you do something else. You say, okay, I don't care about this, but let's say I care about theta. So theta is the thing that's proportional to viscosity. And we are particularly interested in small viscosity. So I put it to be theta equals to 3. Now remember, if you solve for, if you do high Reynolds number flows, then this theta is usually of the order of 10 to the power of minus 6 something. So you may not really care about anything that's numerically of the order of 10 to the power of minus 18, right? And now you solve this thing for omega 3, omega 4, omega 5, and A and B. And the most amazing thing is that this actually has a solution. So there is a magic parameter solution. To this, meaning you get, I mean, you still have this Mach error, so it's not technically first order accurate, and you still have this error tau by the power of 3, which for the viscosities that you're mostly interested in is extremely small, so but still technically it's not first order accurate. Yeah, and it's mathematicians don't allow me to say it is almost first order accurate because this is something that you're not allowed to say, but you made this leading order error extremely small, right? So this means you have a drastic reduction of the error, what you see there, if you look at the solution, of course, the solution must be admissible, meaning that the omegas need to be in a certain range, yeah? And they are not admissible for all sorts of viscosity, but they are admissible for the viscosity that you most care about, namely for when viscosity is small. So they are only admissible up to a certain viscosity, otherwise they become unstable. These equations actually become unconditionally unstable. I mean, conditionally on the viscosity, yes, okay. But this is admissible for small viscosity. And of course, I mean, it's less stable than the regularized one, which is extremely stable, I would say. Less stable than regularization. So, because we are talking about virtual fluids, now this is, if you don't care about theory and you care about the code, then I have some message, I still have some message for you, because this is now important for the implementation. Because some of these rates get very close to zero, then yeah, they can become unstable. And for this reason, we immediately introduced the stabilization for this, which I didn't like from the beginning and I didn't like now. I mean, I have a very simple idea, and unfortunately, this simple limiter is still the only thing that I ever found that actually worked. But it worked out of the box. So the simple idea is, if you have to think about numerics and order of convergences, yeah, here a lot, because this is, we are looking specifically at the leading order error. And now if you implement a limiter on these relaxation rates, then you have to just you have to think about, what can I do that stabilizes this without modifying the order of convergence that I just reached. So you have to design your limiter at a specific order of convergence. Yeah? So then, I mean, and then if you try to have it at a yet higher order, so in order to make less errors, then you discover that it doesn't work. Yeah, so this is, unfortunately, if you find something amazing here, something else that also works, you can please go ahead. But I'm telling you how it's now implemented in VirtualFluids. So what we do is we go to a next page and say we have something like an asymptotic preserving limiter. And this, I showed this only for one example. So say we have, why did I use this stupid example? Okay, let's go with the stupid example. So say we have, how do we relax these cumulants? So we have C120 plus C102 plus omega 3, and I put a small dash here, and we have C120 equilibrium plus C02 equilibrium, which is actually 0, minus C120 minus C102. So these equilibria, they are actually 0. So because they are 0, what we can do is we can write omega 3 is equal to omega 3 dash is equal to omega 3 plus 1 minus omega 3 into the absolute value or the magnitude of C112 plus C102 divided by okay, I have to make yes. Okay, I didn't say this. So in the code, we don't use pure cumulants, but we use cumulants times the density. Yeah, so we don't normalize them. So this is why I have to introduce here the density in this point. Yeah, a density times now comes something they call lambda 3 plus C120 plus C102, and lambda 3 is the limiter parameter. And this is a constant, of course, that we have to do. So, I mean, by this procedure, we found out the actual value for the relaxation rates, but we have the same number of undetermined constants in the method too, because we amend each of the relaxation rates with a limiter parameter that we have to choose empirically, just by stability. So, from asymptotic analysis, we know that C120 plus C102 is of order delta x cube, that such that omega 3 dash is omega 3 plus maybe more accurately it's velocity times, but this also is of order 3, because we assume that velocity is of order 1. I mean, this may be more accurate to say it this way. It's u times delta x cube, and this is sufficiently small such that it will asymptotically disappear when you put this into the leading order error. Yeah, and what it physically then does is you have if these things are much smaller than rho times lambda 3, then omega 3 dash goes to omega 3. So this here is dependent on the shear stress. There's the shear stress in this. So if the shear stress is sufficiently small, you get exactly the value that you want. So if the shear stress is, sorry, that's not the shear stress. It's a second, sorry. So it's not the shear stress, it's a second derivative of velocity. It's a second derivative of velocity. If these second derivatives are sufficiently small, then you get what you asked for. If they are too large, so if they get larger than your value here, so this thing here goes to 1, which is regularization and which is very stable. So by this you go back to a stable version. So if your flow gets too turbulent such that the second derivatives are too large, then automatically your method turns to the stable regularization and remains stable. Suppose that you've chosen omega 3 small enough. Yeah. So then this means that you have to choose this lambda 3 as large as possible and as small as necessary. So for better accuracy, as large as possible. and for better stability as small as necessary. And I cannot tell you how to do this. You have to try it out. I mean, the problem is if you do all these tricks and get to higher and higher and higher order. So what you observe then is you don't get a beautiful curve where you exactly see, oh, this is second order, but you get something pretty. I mean, the error is low, but it does not behave in any nice way anymore. Yeah. So now you are very much on the edge, and therefore it's difficult from theory to determine what value you should put there. Okay, now this actually concludes lecture number 4. How much overtime did I take? I will stop the recording here to start it again.